The screen opens with the sound of thunder rolling across the sky. Dark clouds gather above the eternal city of Rome. Rain begins to fall, slow at first, then heavier, until it becomes a relentless downpour. The camera descends through the storm, moving toward one of the most extraordinary structures ever built by human hands, the Pantheon. We pass through its massive columns, into the vast interior, and then look up. At the very top of the dome, a perfect circular opening, the oculus, invites the sky inside. Rain pours directly through it, cascading into the heart of the building. And yet, the floor does not flood. There is no chaos, no damage. Instead, the water disappears, guided silently through an ancient drainage system hidden beneath the stone. For nearly 2,000 years, it has worked flawlessly. No modern pumps, no electricity, no repairs required, just precision, just understanding. And this is where the mystery begins. Because while ancient structures like the Pantheon continue to stand strong after millennia, many modern buildings, bridges, highways, even entire residential complexes begin to crack, weaken, and fail within just a few decades. 40 years, 50 if we are lucky. So what did they know that we have forgotten? As the camera slowly circles beneath the dome, the narrative deepens. Ancient architecture was never just about stacking stone. It was a science, a discipline rooted in observation, mathematics, and an intimate understanding of nature itself. Every angle, every material, every opening was part of a larger system. A system designed not to resist the environment, but to work with it. Consider the way ancient builders handled water. Rain was not treated as a threat, but as a predictable force, one that could be guided, redirected, and controlled. Floors were subtly curved, channels were carved with invisible precision. Even the smallest detail served a purpose. This was not decoration. This was engineering at its highest level. And then there is the material that changed everything: Roman concrete. At first glance, it appears simple, just a mixture of volcanic ash, lime, and water. But under microscopic analysis, it reveals something astonishing. Unlike modern concrete, which gradually weakens over time, Roman concrete becomes stronger. Yes, stronger. Within its structure are tiny fragments of lime, what scientists call lime clasts. When cracks begin to form, water seeps into these microfractures and triggers a chemical reaction. The lime dissolves, recrystallizes, and fills the gaps with newly formed mineral material. The structure heals itself, slowly, naturally, silently. This is not just durability. This is adaptation. And nowhere is this more evident than in ancient Roman harbors. Along the coastlines of the Mediterranean, massive concrete structures have stood against the relentless assault of saltwater for centuries. In modern construction, salt is the enemy. It corrodes, weakens, destroys. But in these ancient designs, seawater becomes an ally. Minerals within the water react with the volcanic components of the concrete, forming new crystalline structures, reinforcing the material from within. The longer the structure remains in the ocean, the stronger it becomes. Imagine that, a building that grows more resilient with time. As the scene transitions, we leave the shores of Rome and travel east, toward the vast landscapes beneath the Great Wall of China. Here, another secret awaits, one that seems almost impossible at first glance. Rice. Specifically, sticky rice. Ancient Chinese builders developed a unique mortar by combining lime with glutinous rice. At a molecular level, this mixture forms a composite material of remarkable strength and flexibility. The key lies in a component called amylopectin, a complex carbohydrate that binds the structure together, distributing stress and preventing brittleness. The result? Walls that do not simply resist force. They absorb it, they adapt, they endure. This is not primitive construction. This is chemistry, practical, intentional, advanced, and the journey continues. High in the mountains of the Andes Mountains, where the air is thin and the earth itself trembles, we encounter one of the greatest engineering achievements of the ancient world, Machu Picchu. Here, the Inca built without mortar. Massive stone blocks, some weighing several tons, are fitted together with astonishing precision. No gaps, no binding agents, just pure geometry. At first, it seems impossible. But then, the ground begins to shake. Earthquakes. In most structures, seismic energy leads to collapse. Rigid walls crack. Foundations fail. But in Machu Picchu, something extraordinary happens. The stones move, slightly, almost imperceptibly, absorbing the energy of the quake. And when the shaking stops, they settle back into place, unbroken, unshaken, alive. This concept, sometimes described as living masonry, represents a completely different approach to architecture. Instead of fighting against nature, it allows the structure to respond, to shift, to survive. And as we move deeper into history, we arrive at the deserts of Egypt, where the pyramids rise against the horizon with silent authority. Here, the secret is not flexibility, but order, perfectly leveled foundations, precise alignment with cardinal directions, a distribution of weight so carefully calculated that the structures remain stable after thousands of years. Every block placed with intention, every angle measured with care. No excess, no error, only balance. Then, carved directly into the living rock of Ellora Caves, we encounter the Kailasa Temple. A structure unlike any other. It was not built from the ground up. It was carved from the top down, from a single massive block of stone. No joints, no weak points, no margin for error. One mistake, and the entire structure would be ruined. And yet, it stands. A testament to patience, precision, vision. Finally, the journey brings us to medieval Europe, where towering cathedrals reach toward the sky. Structures of breathtaking height and complexity, made possible by innovations such as flying buttresses and advanced drainage systems. These are not just aesthetic features, they are solutions. External supports redistribute weight, allowing walls to rise higher and thinner. Gargoyles, often seen as decorative, serve as water channels, directing rain away from the structure, keeping the stone dry, preserving its integrity. Every element has a function, every detail matters. As the camera slowly pulls back, showing centuries of architecture across continents, one realization becomes impossible to ignore. Ancient engineers were not limited by a lack of technology. They were empowered by a deeper understanding. They studied nature, not to dominate it, but to learn from it. They built structures that could endure not because they were stronger, but because they were smarter. And today, as modern scientists revisit these ancient techniques, a new possibility begins to emerge. The materials of the past may hold the key to the future, from self-healing concrete to sustainable design, from Earth to the Moon, and even Mars. Because if we want to build structures that last for thousands of years, we may need to look backward, to move forward. And perhaps, hidden within stone, water, and time itself, are the answers we've been searching for all along. The screen fades in once more, this time not to a single monument, but to a sequence of structures spanning continents and centuries. From the enduring dome of the Pantheon to the towering ridgelines beneath the Great Wall of China, a pattern begins to emerge. A pattern not of style, but of principle. Ancient engineers, separated by vast distances and cultures, arrived at similar solutions. Not by coincidence, but by understanding the same fundamental truth. A structure is not just an object, it is a system. A system that must interact with forces, gravity, water, temperature, time, and most importantly, change. As the camera moves across a simulated cross-section of a Roman structure, we see microscopic reactions unfolding over decades, even centuries. This is the secret of Roman concrete, not just strength, but evolution. Modern materials are often designed for immediate performance, maximum resistance, maximum efficiency. But in doing so, they sacrifice something essential, the ability to adapt. When stress exceeds their limits, they fail. Abruptly. Catastrophically. Ancient materials behave differently. They respond, they adjust, they endure. And nowhere is this philosophy more evident than in environments where destruction seems inevitable. Along ancient coastlines, Roman maritime structures remain standing despite centuries of wave impact and chemical exposure. Instead of resisting the ocean, they harness it. Salt water triggers chemical processes that strengthen the material over time. In this way, the environment becomes part of the technology, not an enemy, but a partner. As the scene shifts eastward again, we return briefly to the construction techniques behind the Great Wall of China. Zooming into the mortar between stones, we see the complex interaction of organic and inorganic materials. Lime provides rigidity. Sticky rice introduces flexibility. Together, they form a composite capable of distributing stress evenly across the structure. This reduces the risk of sudden failure. It transforms brittleness into resilience, and perhaps most importantly, it reflects a mindset. A willingness to combine observation with experimentation, to use what is available, not just efficiently, but intelligently. This same philosophy echoes through the high-altitude fortresses of the Andes Mountains. At sites like Machu Picchu, the concept of living architecture reaches its peak expression. Each stone is shaped individually, fitted with precision, allowing the entire structure to move as a unified system during seismic events. There is no rigidity, no single point of failure, only balance. This approach challenges one of the core assumptions of modern engineering, that strength comes from resistance. Instead, it suggests that survival comes from flexibility, from adaptation, from movement. As we descend once more into the ancient deserts of Egypt, the camera aligns perfectly with the edges of a pyramid, emphasizing symmetry and proportion. Here, the principle shifts again, from flexibility to precision. The foundation is everything. Even the smallest deviation in leveling would have amplified over the height of the structure, leading to instability. But the ancient builders achieved near-perfect alignment using tools and techniques that remain partially unexplained. The result is a structure that distributes weight so efficiently that it has remained intact for thousands of years, not because it resists time, but because it respects it. And then, carved silently into the volcanic rock of Ellora Caves, the Kailasa Temple reveals yet another dimension of ancient mastery. By removing material instead of assembling it, the builders eliminated structural weaknesses entirely. There are no joints to fail, no seams to separate. The mountain itself becomes the building, a single continuous form, unbroken. This technique requires not just skill, but vision. The entire structure must be planned in advance, every detail understood before the first cut is made. It is engineering without correction, creation without margin for error. And yet, it was done. As the final sequence unfolds, towering Gothic cathedrals rise into view across Europe. Their spires pierce the sky, supported by systems that appear almost delicate, but are in fact the result of precise force distribution. Flying buttresses channel weight outward, elevated drainage systems keep walls dry, gargoyles extend outward, directing water away from vulnerable surfaces. These are not ornaments, they are calculations, visible expressions of invisible forces. And when we step back, when we look at all these achievements together, a profound realization takes shape. Ancient engineering was never about domination, it was about integration. Integration with nature, with materials, with time itself. Modern construction, in contrast, often prioritizes speed, efficiency, immediate results. But in doing so, it sometimes overlooks the deeper principles that allowed ancient structures to endure for millennia, principles that are now being rediscovered. Today, scientists and engineers are studying Roman concrete formulas to develop self-healing materials. They are analyzing ancient drainage systems to design more sustainable cities. They are revisiting the geometry of megalithic structures to understand how to build in extreme environments, even beyond Earth. Because as humanity prepares for construction on the Moon and Mars, the challenges become familiar. Extreme temperatures, limited resources, isolation. In these conditions, the lessons of ancient engineering become not just relevant, but essential. Build with what you have. Design for change. Think in centuries, not decades. As the screen slowly fades to black, one final message remains. The greatest technologies are not always the most complex. Sometimes, they are the most patient, hidden in stone, refined by water, perfected by time. Ancient engineers did not just build structures, they built systems that could survive the future. And perhaps, if we listen closely enough, they are still teaching us how.